Good evening, everyone. We are in the last problem-solving session of the course, Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. This session will be more of course summary followed by problem-solving session. Let me share my screen. Is my screen visible?
Yes. Sir, it is visible.
Okay. Yeah. Thank you. So we have completed 12 weeks, which means 12 problem-solving sessions, one for each week for this course, and this will be an additional 1 hour session where we'll summarize what we have discussed throughout these 12 sessions, and if time permits, we can solve a few problems at the end. Yeah, so this course is about digital control in switch mode power converters and FPGA-based prototyping. So the course summary is as follows. So in week 1, we had a very brief introduction to digital control and switch mode power converter. So we have seen what are the products where digital control is needed and why digital control is needed, and other aspects of what will be the advantages, what will be the disadvantages, what are the challenges, what are the disadvantages, and how to tackle those disadvantages. It was more like an introduction, and we had seen buck converter example, and a few control architectures were revised in this week and followed by week 2. So this was basically most of the part was introduction. And in week 2, we had gone into the fixed and variable frequency digital control architectures. So where we have rigorously discussed about it has again 2 parts. The first part is the digital control architectures, and where we have discussed fixed frequency digital control architectures, mainly the voltage mode control, current mode control. And in the variable frequency digital control architectures, we again discussed the voltage mode based, which is voltage based constant on time, constant off time, and then mixed signal constant on time, constant off time. And followed by, we have also discussed about the sampling methods. So what sampling methods are used and why they should be used, and how many times we can sample in a cycle, and what happens if we sample more number of times, and what happens if we sample less number of times, what are its challenges, what are the issues, and all these aspects we had discussed in week 2. And apart from this, we have also seen mainly the nomenclature. Like, suppose an architecture is given, so what is the nomenclature that we use to define that? What if we say leading edge, and what if I say trailing edge? What do we mean by leading edge, and what do we mean by trailing edge? And what is interval 1 sampling and interval 2 sampling? So all these interval 1, 2 sampling. So all these things we had discussed, and we had also solved few problems based on the understanding these concepts. So provided like a digital control architecture is given, so how can we identify which architecture it is? So how will we know it is voltage based or current based? How will we know it is analog? So we have also discussed about these aspects, whether it is analog. Okay, let me use a different dark color. So we have also discussed whether it is analog or mixed signal or fully digital. So if your architecture is given, how to identify whether it is fully analog, or how to identify whether it is mixed signal, or how to identify whether it is fully digital. All these things we have done in the week 2, and this is very fundamental week, because without knowing these architectures as well as the nomenclature, interval 1 sampling, leading edge, trailing edge, different sampling methods, it would be very difficult to follow the next week. So this week is very fundamental, and if you are having any confusion regarding this nomenclature, kindly go through the week 2 lectures, or you can go through our week 2 session. And then in week 3, so week 3 is just the MATLAB implementation of whatever we have discussed here. So whatever we have discussed in this week, we have implemented the same in MATLAB. So when we moved into MATLAB, the very first question is how to implement MATLAB models of digital control architecture. So that was our first question. So then we have discussed something called zero order hold, which will work like an ADC. And for zero order hold, at what time we should take the sample. And then the second question arose, which is whether it should be uniform sampling or event-based sampling. And then two more questions will arise. What is event-based sampling and what is event-based uniform sampling and what is event-based sampling and where it should be used. So then we have discussed that uniform sampling is like a fixed frequency. So we use it for fixed frequency control techniques. And this is for variable frequency. As we are taking one sample per cycle and as the frequency is varied, if you want to take one sample per cycle, the event will occur only once in a cycle. If you take uniform, either we could be taking more number of samples per cycle, or maybe we could be taking one sample for few cycles. So which is again not uniform, it should be synchronized with the clock. So that's why we are doing the event synchronized clock. So whenever that inductor hits the peak or hits the valley or voltage hits the reference or hits the like peak reference or valley reference, based on that we are getting the event, and using that we are sampling, which will work like an ADC. And then the main block, which is the digital PID controller. So there is a by default digital PID controller block in the MATLAB, which you are again, we can use that block and we can implement everything except when we go into the variable frequency, where the reference has to be computed once in a cycle. If you use the custom, not a custom, the by default MATLAB digital PID block, it will update like a uniformly. So it will have a switching frequency. So according to that time period of the switching frequency, it will keep on updating. So it could be multiple times in a switching cycle, or it could update once for multiple cycles, which again we don't want. We want it to be updated once in a cycle. So for variable frequency, it should be event triggered. So our PID controller should be event triggered. But whatever the block that is already available in MATLAB, it is not event triggered. It will be triggered by the frequency clock that we have to enter. So it is not event triggered. So for that reason, we have made custom digital PID block using the difference equation. So first we got the MATLAB digital PID expression, and using the difference equation, we have implemented the digital PID controller in MATLAB, which is again custom. So it could be either uniform sampling or it could be event-based sampling. So it could be uniform sampling or it could be event-based sampling. So accordingly, we can tune it. So now everything is in our control. How many times I want it to be updated? Everything is in our control because it is custom. So we can play with that. And there is also enable as well as trigger. So when we make a subsystem, it has two inputs. One is enable and one is trigger. So enable will try to turn it on or off. So if enable is on, enable is 1, it will be on. If it is 0, it will be off. And trigger will say when to start the computation. So whenever it sees a trigger, then it will start the computation. Until that time, it will hold that value. So if you want once in a cycle, at what instant you want it to be like computed. So at that instant, you either give a clock edge or event edge, and accordingly it will start computing and it will compute the value. And then in week 4, we had discussed about the different modeling techniques as well as model validation using MATLAB. So we have discussed about different modeling techniques, mainly the large signal modeling, small signal modeling. And these two are again discrete time. So I will call discrete time DT. And we have also seen continuous time with delay, and discrete time. And we have seen which one should be used and what are the limitations of the models, which will be more accurate and which will be more easy to deal with. All these aspects we have discussed in week 4. Now coming to week 5. So week 5, then we slowly moved on to the design. So then we slowly moved on to design. So we have discussed about frequency and time domain digital control approaches. So we have again taken multiple case studies. One is the voltage mode control and the other one is the current mode control. And in each of it, we have discussed multiple things. In voltage mode control, we have discussed two. One is the pole zero cancellation. The other one is the alternate method. And in current mode, we have discussed again two methods. One is the pole zero cancellation, which we would like to say pole zero cancellation or without load feed forward, because there is no load feed forward, and or we can say pole zero cancellation. It is up to us. So either we can say without load feed forward and with load feed forward are the two techniques that we have discussed, or we can also say one is the pole zero cancellation, small signal based. And then we have discussed about the large signal tuning, which is again with load feed forward, and how to design it, all the aspects we have discussed in this week. So we have started with the continuous time model. So in week 4, we have fixed that continuous time delay should be good enough to design controller. And discrete time model should be used to ensure whether the system is stable, because continuous time with delay model fails to do so. So this for controller design and this for stability. So for controller design, again small signal, we used continuous time model with delay, because there will be delay of the ADC DPWM delay. So the tau d is sampling delay plus on time t on. So this is the total delay. We have considered that, and we have validated that it is matching with the discrete time model. And then we have said that it is good enough to design a controller, because it is easy for us to design and imagine the poles location, pole zero cancellation, everything, which would be much difficult if you go into the Z domain. Whereas stability, when it comes to stability, continuous time with delay model is not sufficient to capture all the instabilities. And for that reason, we should go for discrete time model. So we have finalized that we'll design the controller with continuous time with delay. And again, it has bandwidth limitation, 1/10 of the switching frequency. And then discrete time model, we moved to decide the stability. Sir, I have a doubt. Can I ask now or at the end? Yeah, you may ask now.
And this alternative approach in the voltage mode control, we discussed it for buck converter, right?
Yes.
Can we apply the same for boost as well?
Yes. I'm not exactly sure, but I think recently one of our lab mates have published a paper. It must have boost converter as well, alternate method, large signal tuning. I'm not exactly sure about the name, but I'll check with them and I can share the link for that paper. If you are interested, just drop a message in LinkedIn so that I'll get that paper link and I can share.
Okay, sir.
Okay.
Thank you.
Mhm.
Sir, like we all discussed this. I am clear with the pole zero cancellation,
Okay.
but I'm not sure about this alternate method
Okay. So
for
in
boost converter.
Okay, for boost converting. Okay. First, we'll do one thing. You just drop me a message in LinkedIn. I'll share the paper. So if you are interested, again, it is not needed for your exam. So don't waste your time. Don't waste your preparation time. You may go through later. But even after going through the paper, if you have doubts, I can directly make you contact that author of the paper, or I can discuss with you.
Okay, sir.
But I'll share
Thank
the
you.
paper. Just drop me a LinkedIn message, or you can mail
Okay,
me.
sir. Sure.
And in the week 6, we went to the digital control implementation and FPGA-based prototyping. So we started with the signal conditioning. What type of signal conditioning circuit we have used? What are the ADCs and DACs that we have used? And their corresponding drivers, comparators, and the schematic of the power stage. How do we do current sensing? We had discussed multiple methods of current sensing. One is the non-isolated one, and the other one is the isolated one. So how to or what are the different techniques available in current sensing when it comes to non-isolated, or when it comes to isolated, when isolated is needed. And we have done non-isolated current sensing, which is again resistive sensing. So when we do the resistive sensing, what will be the gain, how to calculate the gain, what is the circuit, how to get the gain, and all those gains should be again included while writing the Verilog code also. So here all this introduction about the signal conditioning, everything, before we move into the actual hardware and Verilog coding, we discussed about the signal conditioning part. And in week 7, we went to the Verilog and simulation using Xilinx Webpack. So the software name is ISC. So you can always use this software. It is a very good software, and it is a free software. So you can, only thing you have to create an account and get the license file, and the license file is free, and then you can use it, and you can use it for any FPGA if that FPGA can be coded with ISC. So we have discussed about Verilog. So why we used Verilog and what are the basic building blocks of Verilog, how to write the code in Verilog, what are different abstraction levels, and how to write a module, how to instantiate sub-modules. And we have discussed about few examples like 4-bit triple carry adder. We have broken down into single bit adder, and then with adder circuit we have broken down into gates. So we have discussed about the abstraction and top-down design methodology. And then we have also seen how to simulate using Xilinx, how to create project, and how to run it. All those things we have seen in week 7. After learning the Verilog part, we have moved into the week 8, which is about the digital control implementation using fixed point arithmetic and Verilog HDL. So the main important aspect here is the fixed point arithmetic. So we are not using floating point. We are using fixed point because floating point would be much difficult to deal with. And just to start, fixed point arithmetic is good and it is widely used. And we have also discussed about the concept of Q format. So what is Q format? Q format is a virtual dot for us, not for the compiler. Compiler will not see any dot. So that Q format is a virtual dot for us. So that every time when we have a n-bit number, using that Q format, we'll get to know the actual quantized voltage. So this is for us to understand the actual quantized voltage information. Quantized voltage information can be obtained using that Q format. And here we have discussed digital voltage mode control implementation, mixed signal current mode control implementation, and digital PSM implementation as well. And you need not by heart line by line coding, and you should not also by heart the code part. Code part is mainly to make you understand the concept, and we have provided so that you can try, and then if you are struggling, then you can take the code, but do not by heart the code. It is just a logic. So we are implementing the logic, and there could be multiple ways for implementing the logic when it comes to code. So this is not the only code that should be used. The logic is same, but you are free to write in a way that you want it to be written. But this is like a basis for you. So if you struggle to write the code, then you can refer this code, but don't by heart it, understand the code. And then in week 9, we discussed about the microcontroller. So this is an introductory session about microcontrollers. So we discussed about 2 types of microcontrollers that are widely used in the industry. One is the STM microcontroller, and the other one is the Texas. So STM32. So again, we have discussed why STM32, because it is suitable for our mixed signal domain. So that is the main part. So we have discussed about STM32 microcontroller and C2000 microcontroller. So they have built-in ADCs, DSS comparators, different type of counters. So what are their architectural advantages that they are offering, and some of the microcontrollers are specific to some applications. So in that case, apart from the ADC, DSC, sometimes they may include the switches, say for motor driver application, they will include some hardware that is needed to implement. So in this way, they will reduce the area. So it will be improved in 2 ways. One is the power density as well as efficiency. So in STM32, we have discussed about the LLC implementation, where they have showed the live demonstration, and we have also seen the hardware and some details of the NLC. And Texas Instruments people have shown their implementation of PFC, proton pump PFC, and we have also discussed about the same. And in week 10, we went for the steps for FPGA prototyping of digital voltage mode and current mode control. So this is like again something that we could relate to what we have learned in previous week. So again, this is more details of digital voltage mode control and current mode control, but this is variable frequency. So we have seen the variable frequency implementation of digital voltage mode and current mode control. So mainly the variable frequency aspects we had covered in this week. And in week 11, design and validation case studies using digital voltage mode and current mode control. So again, we have there was a recap of design case studies, and then we have mapped the MATLAB versus hardware. So what are models that we have developed? How good are they when we compare it with the hardware? Are they sufficiently good enough so we can predict the hardware behavior using the simulation? Yes, to some extent, but we have also discussed it will not exactly match because there could be some parametric mismatch from the inductor value that we have selected and the actual inductor value. There will be tolerance limits. So there will be some parametric mismatch always, and there could be some unmodeled dynamics which we are not capturing and not including in the simulation. So we can use SPICE models with other softwares, and it could predict much better, somewhat better than MATLAB, but it is again user choice. But MATLAB is sufficient and good enough. And in week 12, we had hardware case studies of advanced digital control architectures as well as course summary. So in this week, which is the last week, we have discussed day before yesterday. Here we have concentrated on the digital control architectures, mainly the multi-mode. So we have discussed why multi-mode is needed and what are the advantages of multi-mode architectures and why we are using that, because to improve the light load efficiency. And we have also discussed two types of multi-mode architectures. One is the voltage based and the other one is the current based. So we have voltage based multi-mode as well as current based multi-mode. And in voltage based, we have seen DPSM and DPWM. So voltage mode control and voltage based PSM. And in the current mode, we have mixed signal current mode control, but that is at the high current. So at low current, we have adaptive on 10. And then followed by mixed signal current mode control. So this is just a like a brief summary, but let us go in details and we'll again go through what exactly we have discussed individually in every week. So till now, if you have any doubts, you may ask. As this is a summary, you might not have doubts, but if you have any doubts, don't hesitate to ask. You can stop at any time. Okay, then we can continue. So week 1, again, it is introduction to digital control for switchboard power converters. And if you are working in any topic, I would suggest you to check what are the digital control ICs that they are using. Say if you are working in some battery management or battery charger application, just check what are the digital control ICs that are being used in like by different companies, what are the ICs that are available. And then you can go through their datasheet and check what type of control architecture are they using, whether it is voltage mode control, current mode control. And if they give any information, see how good their control is working. And you may also find some ICs are using multi-mode architecture, then you can see, and then you can relate to. So this course is not just for the course purpose, but you can apply in your real life or in your career as well, or wherever, whichever industry you are working in. So you can correlate whatever you have learned from this course with the work that you are doing or whether you will be doing in the future. So you can correlate, and this course will always help you. Just don't think about in terms of grades, but this course is rich in content, and it has a wide range of applications in many domains. So I take this course seriously, and you can also see different kinds of solutions where the digital control is being used. And then we have discussed about levels of digitization. One is the housekeeping, where DAC will be using, and reference we will be
Hello,
giving. Hello, yes.
sir. You check to the which VMC or CMC you said.
Yes.
It is for only for a DC-DC converter,
Or
like voltage
DCS.
mode control or current.
Yeah, like depending upon what type of control they are using. So here, say PFC, they will
Sir,
also be using current mode control.
if it is like three-phase inverter, can we use the VMC or CMC there?
I'm not exactly sure whether they'll use current mode control, but they'll use this phase shifted pulse width modulation, which is PWM. So they'll have these PWM signals which are phase shifted because it is for three phase, and there will be a sine wave, and then they'll compare. See, like in our course, we have not shown any sine wave, but we have taught that there will be a ramp and there will be a control voltage coming from the controller. But in the case of whatever they will be doing, they'll have very high frequency sawtooth waveform, very high frequency sawtooth waveform, and on top of that, there will be a sine wave, so which will be generating the gate pulse. So it will not exactly be same, but you will have some idea. See, different architectures might be using different type of like implementation, but moreover, it will remain the same. You can correlate. It will not exactly be the same, but you can correlate to what you have learned here, and you can still apply in other domains.
Okay, sir, but this modes what you are saying, like CMC or VMC, I am thinking that it is restricted for DC-DC,
No,
I
no, no, no,
think.
like, no. In PFC also they use
Okay,
current mode control and voltage mode control. And here in
okay, sir.
DC-DC, the current is triangular, but in the case of AC, it will be sine. So there the reference itself is also changing. See, when we say current mode control, you should not always think that, okay, there is this constant I reference and inductor current is at steady state. Because it is DC, it is happening so. But in the case of AC, the reference will be a sine and the inductor current will also be sine. But the way of implementation, it is same, but the waveform is different. So there will be slight changes. I'm not saying the exact thing you can implement in the other thing. There will be slight changes according to the application where we are applying it, but the the crux of the concept will remain the same. So the code concept will remain the same, and it will be adapted to whatever application you are applying it. Okay. And
Okay,
then,
sir. Thank you.
yeah, then we have also discussed about the housekeeping methods and mixed signal, fully digital control solutions, and some commercial digital solutions were also discussed. And we have also seen some digital control implementation platforms. And week one is mainly about the introduction. Now coming to week two, as we have discussed, I'll go somewhat quick because we have discussed. So the main aspect was the fixed frequency as well as variable frequency modulation techniques. And then we have discussed what is uniform and what is event-based sampling and why it is being used and where they are being used. And then we have seen the fixed frequency digital control solutions like voltage mode control, current mode control, and we have discussed about digital pulse width modulator architectures. And we have discussed three such things. Let me use different color. So we have discussed three such things. One is the counter-based DPWM, and the other one is the delay line-based DPWM. The other one was hybrid DPWM. And for this course, we are using counter-based because for this, the cost of the hardware will increase, even though it is much better than counter-based. But considering the cost, counter-based is widely used because in delay line and hybrid, the number of buffers as the number of bits increase, it will exponentially be increased. So we have used counter-based, and then we discussed about variable frequency digital control solutions, and then we get to know that it is the event-based sampling will be used in variable frequency, and the other implementation aspects we have also discussed. And mainly the nomenclature, trailing edge, leading edge, interval 1 sampling, interval 2 sampling, all these aspects. In week 3, as we discussed, it is more of MATLAB models. So we started with the MATLAB model development flow. We have all the models have the same skeleton. One is the power stage, and the other one is the controller stage. So power stage remains same, which happens to be buck converter in this course, but it can change depending upon the application where you are working in. And accordingly, the controller has to be tuned, and power stage remains same for your application. Only the controller stage will change. So if you are working in some other converter, you can, after this course, you can start designing the controller and check the MATLAB simulation. So we have discussed different type of controllers. And then we discussed about the custom MATLAB model. And we have asked the question why custom is needed. And we have got the reason that for variable frequency we need event-based. For that reason we need custom. And how we have developed this, we have developed using the difference equation. And then we have implemented the fixed frequency, and then we have implemented the variable frequency. Variable frequency, again, we have discussed in some border cases, the system might collapse to 0, or it could keep on increasing. So then we said for constant on time, we need minimum off time. And for constant off time, we need minimum on time. So we have discussed why it is needed and how it can be implemented. And then we went to the modeling techniques. So in modeling techniques, first we have started with the continuous time small signal modeling techniques, and then continuous time modeling in digital, which means continuous time with delay. So we have considered the entire delay as a lump delay. So we have added the delay in the loop, and we have considered a single delay, which is tau d. So we have represent the entire delay, total delay, as tau d, and then we have implemented in the loop, and accordingly we have designed the controller considering the tau d. So this tau d will be affected in phase only. Gain will still remain the same because e to the power minus h tau d has a magnitude of 1, but it will affect on the phase. So then the controller values change accordingly, because in order to achieve the phase margin of 60 degrees, when use the continuous time model, when use continuous time with delay model, it will not result in the same values because this will affect the phase margin. And then we have discussed about the discrete time large signal models. So what is a large signal model? And then from there, we have put up the large signal model, and we got the small signal models. And then we had done a comparative assessment of continuous time as well as continuous time with delay as well as discrete time models. And then we had come to a conclusion that continuous time with delay will make our lives much easier and simple when it comes to the controller design. Whereas it is not quite accurate when it comes to the stability aspects, for which we should go with the discrete time model for stability. So when we have designed a controller, and if you want to know, first thing is you can simulate and check whether the system is stable. But before simulating, if you want to do it mathematically, then you can use the discrete time small signal model and then find the eigenvalues and see whether they're inside the unit circle or not. And week 5 is the design techniques, where we have discussed about controller design. So to start with, we have discussed the continuous time small signal model design, which means the continuous time with delay, because we have came to the conclusion that it is simpler and it is sufficient. And then we have discussed about the indirect frequency domains in voltage mode as well as current mode control. So we have designed the PI controller as well as PID controller. So in voltage mode control, it happens to be PID, and in current mode control, it happens to be PI, depending upon the requirement. And then we have validated the small signal models as well as large signal models using switch simulation. So this is again the MATLAB simulation. We have compared and checked, yeah, it is perfectly matching, which means our model that we have derived is correct. And then we have also proposed alternate design method for digital voltage mode control, which is improving our response because it has that derivative effect. And then we discussed about the large signal based tuning, mainly the trajectory-based tuning. For fast transient response, and we have seen that it is much superior compared to the small signal model because it has load feed forward, and we are considering the large signal model or large signal tuning pushing the bandwidth. Whereas in the case of small signal, the bandwidth is limited to FSW by 10, which can be improved in the case of large signal tuning. And then in week 6, we discussed about details of power stage and signal conditioning circuits. So first we started with the ADC, what type of ADC DAC we have used. We have opened the datasheet and checked where are the details, how we get to know the ADC DAC, and what are the other signal conditioning circuits like current sensing. Then we moved on to the current sensing technique for high frequency and high power switchboard power converter. So the current sensing for isolated as well as non-isolated we have discussed. And then few guidelines for PCB, which I have not covered, which SAR has covered. And for power stage as well as signal conditioning circuit. So SAR has shown few schematics. And then few steps for FPGA-based controller implementation, which we have again done in week 7 as well. So in week 7, it is the proper Verilog introduction class where we started with the introduction of basics to the Verilog HDL language, and then we went on to the Verilog HDL programming also. And then we have discussed different levels of abstraction, the behavioral model, structural model, and we have seen how to see the register transfer logic in Xilinx ISC, how to view that, and how to simulate it in Xilinx ISC platform, how to create a new project and how to run the code. All these aspects we have checked in week 7. And the very crucial is the fixed point arithmetic. So there are 3 lectures, I guess. If you are still confused, you just go through these lectures. So 2 lectures on fixed point arithmetic, or 1 lecture on this and 1 lecture on this. So these are very important. So you please go through that if you still have any confusion. And concept of queue format is the virtual dot. There is less than a minute, so if this meeting can quickly join back, so we can continue the discussion. So this is that virtual dot that we are keeping so that we can get to know the information of the quantized voltage. Okay. So this is all about week 7. Now, if we move on to the week 8, where we have discussed the Verilog HDL-based synthesis of digital voltage mode control and current mode control. So in week 8, we have discussed the top-down design methodology for Verilog HDL-based synthesis for voltage mode control, current mode control, and pulse skipping modulation. And then we have, so the digital voltage mode control, current mode control, and then.
Yes, sir, it is visible now.
Then we have also discussed the Verilog HDL-based synthesis and how to design the PI controller as well as PID controller using the fixed point arithmetic as well as queue format in Verilog HDL. And then we discussed digital PSM control, the top-down design methodology, and also the Verilog HDL-based synthesis. And in week 9, we have discussed about the microcontroller, digital controller implementation using STM32 as well as C2000 microcontroller. First, we have discussed some aspects of STM microcontroller, how to select STM32 microcontroller. And then we had discussed some case studies using design STM microcontroller, and I have shown the demonstration of LED blinking as well as the dead time QHQL with dead time. And we have seen the waveforms in the oscilloscope, and we also discussed how we can get the information of duty ratio and frequency from the oscilloscope itself. And some design aspects of the LNC converter has been discussed. STM people have shown the live demonstration of LLC converter, how to turn it on and how to turn it off, how to get the efficiency information, and how they're turning on the LLC, different kinds of load transient, all these aspects they have discussed. And for Texas Instruments, we have discussed a few aspects of the C2000 microcontroller, and we have also seen some products out there. We have opened their datasheet and we have seen how they are using their microcontroller. So it is basically a type of card. So this card, they'll be connected to the power stage at some point, and they'll dump the code into the microcontroller and it will run. And then we have also seen some example case studies using C2000 microcontroller. And in week 10, we have steps for FPGA implementation of digital voltage mode control as well as current mode control. So for steps we have seen, mainly this is for the variable frequency, because fixed frequency we have already discussed. So this is mainly for the variable frequency. So in the variable frequency, first we have shown the experimental implementation, how SAR is implementing. So there is a laptop which is connected to the FPGA. So from the laptop, we are dumping the code to the FPGA. On top of the FPGA, there is signal conditioning, and this entire module is connected to the power stage, and the oscilloscope probes are connected to the power stage or signal conditioning. So first the code is dumped into the FPGA, and now the FPGA has the code. So there is an interaction between the power stage, signal conditioning board and FPGA, and there is power supply as well, which is powering up the signal conditioning board and power stage. And when the code is running and when the converter is operating in the closed loop, then we are viewing the waveforms in the oscilloscope. And then we discussed about constant off-time or on-time off-time digital control, voltage-based as well as current-based. Then we discussed about the constant on-time mixed signal current control. So this is the voltage-based, and then we moved on to the current-based. And we have also discussed adapt on-time because it is mainly for the light load. This is a light load modulation technique. So we have also discussed this rigorously, and then we had seen some hardware implementation and as well as experimental case study. So we have seen the frequency dependent on the input voltage, and we have seen how in adapt on time it is adapting the on time so that the ripple remains same. So all these aspects, dependency on the V input, how we are tackling the challenge in the case of adapt on time were discussed. And in week 11, it is mainly the design and hardware implementation of digital voltage mode control and current mode control. So first we have seen the steps. This is like a recap of what we have learned in week 5, which is a design. And then we have seen the output impedance analysis. So we got to know that output impedance shapes the trajectory of voltage when there is a transient. So in order to shape that analysis or shape that trajectory, we should have the information of the output impedance, and then we have to shape the output impedance, which will shape our response. And we have seen that in the case of load current feed forward, there is very less overshoot, and ideally there will not be any overshoot. But in our case, there will be slight overshoot because we are may not get the exact current information, and because of which the overshoot is again very negligible overshoot, because the output impedance is almost zero, which means the voltage will not react to any step transient. And we have seen 2 case studies. One is small step up and the other one is large step up. And we have seen that in either of the cases, voltage undershoot is very less, almost negligible. And then for design aspects, we have validated the simulation versus experimental, mainly the MATLAB versus hardware. And then we have seen the HDL implementation of digital voltage mode control and current mode control. And then we have seen few hardware implementation as well as experimental case studies in week 11. Coming to the week 12, which is the last week, final week of this course, which we have discussed recently, the multi-mode digital control and hardware implementation. So why the multi-mode is needed? So it has one light load control technique plus one full load or high load. So at light load, it is operating in one control architecture, and high load it is shifting to the other. So we have also discussed about the spread spectrum, and we have seen the FFT and how it is getting distributed, how it is spreading, and how to implement that in the Verilog code. We have seen it will have 2 frequencies. Either it will be FSW1 to 1 to 1 2, or it will be FSW1 for 10 number of cycles, or and FSW2 for next 10 number of cycles. And we have seen FFT for 20 cycles, which is like 10 FSW1 and 10 FSW2. So we have seen that for fixed frequency, because in variable frequency is varying and we do not have control on the frequency because it is coming from the closed loop. So this can only be done for fixed frequency. And then we have seen the Verilog HDL implementation of the same. And then we have discussed about the voltage mode PWM PSM. So one is the voltage mode and the other one is the current mode. So in voltage mode, we have PWM PSM, and in the current mode, we have mixed signal peak current mode control, followed by adapt to on time. So on time is for light load, and which is pulse frequency modulation, because the frequency is varying and we are using adapt to on time, and we are free to use any light load control architecture which can improve the efficiency. It does not have to be always PSMPWM. It can be the other way around also. And in the current mode, we have selected mixed signal peak current mode control and adapt on time, which happens to be again peak current mode control. And we have seen the hardware Verilog HDL implementation as well as the hardware implementation. So this completes our summary, and I'll quickly go through the problem solving session. So I'll give you the hint, but I'll not solve now. So let us not solve. Maybe you can solve later, but I'll give you a hint how to solve the problems, because the hint is again given in the PPT itself. So as these slides will be shared, you can solve them. And I have not solved, so I have not given the answers, but you can solve. And if you have contact of each other, you may discuss with each other and see whether you are getting the right solution or not. So I have selected a few problems from few weeks. I think I have given around 6 such problems. So let us see. But I'll only give the hint, and I'll ask you to solve, because in the 12-week problem solving session I have solved. So I'll not be solving. And these are taken from our problem solving sessions only. So if you face any difficulty, you can go to that week and have a look at how we have solved that. So in this question, we are giving a DPWM counter-based DPWM, and I'm asking what should be the value of NR. So what should be the value of NR if I'm using a 100 megahertz clock? So this will be 10 nanosecond. And what is the value of TS? They have given 1 microsecond. So what should be the value of NR? And we know the relation between them, which is QD is T clock by TS equals to 1 by NR. So T clock is given, TS is given, and you can calculate the value of NR. So if NR is X, it will be modulo X minus 1. See, if NR is 8, it will be modulo 7 counter. So accordingly, you will get the value of NR. So depending upon the frequency, the counter value will change. And in the second part, I have asked multiple questions, and this is again taken from week 2, where we have rigorously studied about the architecture. So this is a valley current mode control and event. So valley event means constant on time. So is this analog, mixed signal, or fully digital? Mixed signal. And fixed frequency or variable frequency? Variable frequency. And constant on time or constant off time? Constant on time. And the next question will be, is this voltage or current control? Current control, because current is involved. Peak or valley? It is valley. So sampling, uniform or event. So is this trailing edge or leading edge? It is leading edge, because it is a valley current mode control. The edge will be leading. So it is a mixed signal, constant on time, leading edge, current mode control, and event-based sampling is used. And this is one such examples. You can ask the same question to other architecture. So you can take an architecture, you can ask the same questions to yourself, and you can figure out what control architecture it is. And
Sir, I have a question.
yeah.
Sir, like in this case, how we are saying it is constant on time because it is valley, we are
Yes.
saying it is constant on time. Is
Yes.
that the thing?
Yes. And from the
Okay.
comparator information also I can tell.
Okay, sir, but how we can say that it is the leading edge?
See, constant on time, if I draw the steady state waveform, so let me draw. So this is the I reference. And I'll have constant on time, off time, on time, off time. So this is IL. So is my IL leading, or like is it above I reference or below I reference?
It is above I
So
reference.
it is leading edge, because the edge is above the reference. Whereas in the case of constant off time, the edge I reference will be here. And if I take other color, the inductor current will be on time and constant off time, on time, constant off time. So here it is trailing. So it is trailing edge, and this is leading edge.
Sir, what I have gone through is like if I'm comparing a rising edge ramp with the constant term,
Mm-hmm.
with the constant value. Based on the constant value, the trailing edge depends, right?
Yes, yes.
That aspect I have, sir, but I'm unable to correlate that thing with this leading edge and
Okay,
trailing edge.
it's okay. So I'll explain in the terms how we have understood. So here, what is happening? So the on time is coming. So the during the rising edge of the on time, it is hitting the reference, and the off time it is constant, right? So whenever the rising edge is hitting the I reference, it is getting reset, and then it is turned off for constant off time, and again it is hitting. Whereas in this case, if I use a different color, green color, it is turned on for off time, constant on time. And when it is turning off, whenever it is hitting this, at that moment, it is again turned on for constant on time. So here, the rising edge is hitting the reference. Here, the falling edge is hitting the reference. Now, is that clear?
Okay, sir, clear.
That is
Thank you.
one way, but the way which could be easy is whether I reference is above IL or not. If I reference is above, IL is below, IL is trailing, and if IL is above the I reference, it is leading. So depending upon like your ease of understanding. So now you know both the ways. So it is up to you which way you would like to use.
Okay, sir. Thank
Okay.
you.
Yeah. So in the problem 3, it is the dual slope ADC, which I have taken from week 6, I guess. So we have understood how dual slope is working. So first it will be turned on with the V in for known time, and then it will be turned off, or I could say negative V reference. So it will discharge for unknown amount of time. And from the waveform, we got this expression. So N is N reference into V in star by V reference. So if you substitute these values, you will get the value of N. And depending upon the value of N, the output of the ADC depends. Say if it is a 3-bit, then and N value is 7, the bits will be 111. If it is 6, it will be 110. So accordingly, you can get the output of the ADC. So that is the problem 3. And problem 4, I have asked the combinational logic for this. So if you go, it has a module, inputs are ABC, output is F. So this is the declaration. They are using 2 wires. So the first wire is XNOR of AB. So let me draw with the black color. So this is XOR, and if I put a NOT, this becomes XNOR, which is X, and these are AB, this X, and there is a Y, OR of B and C. So there is a OR of B and C. So this has B, and this also has B. So this is B, this is A, and this is C. These two are X and Y, and the AND operation of X and Y. So if we write the names, this is A, this is B, this is C, this is X, this is Y, this is F. So if they give time like diagram of ABC when A is changing from 0 to 1, 1 to 0, you can get the expression of F in terms of ABC, and from that expression you can see how F is varying with varying ABC. So, but it can be other way around. I can also give you this, then I will give you 4 options. So I can change XNOR of YAB, XPC, or OR gate, AND gate, and I'll ask you which of the following Verilog code is for this circuit. Then you have to select the corresponding Verilog. So it could be either way. You can practice in either way. And when you are not aware that whether your code is working correct or not, then you can go to that Xilinx ISC platform. You can simulate it and check whether it is working accordingly or not. But don't waste too much time. Just spend some time on ISC as well so that you'll get to know. But don't waste too much time in simulation as well, because you might not get extra time for preparation. So manage your time accordingly. So it should be simulation as well as theoretical, as well as mathematical. So if you plan to solve directly in the exam, then you'll face difficulty because you might do calculation mistakes. So I suggest you to do the calculations before, so it could be like a practice, and in the exam you can directly solve. Is someone asking something? So in the problem 5, I have asked on Q format. So if KP is given and the Q format is given, it is 10 bits. So whatever may be the Q format, the sum should be 10. So in this Q format, what is the representation of KP? In this Q format, what is the representation of K? In this form, what is the representation of KD? Again, this is taken from week 7, where we have discussed about the fixed point arithmetic as well as the concept of Q format, and I have solved such problems in that week. So I'm just revising this, so I'll not be solving it. But if you face any difficulty, you can go through our weeks on problem solving session. And this is the building block for the entire course that we are writing, because everything is having a Q format. So you should understand the Q format very thoroughly. And if you have any difficulties, you go through our lecture or you can go through our session as well. And coming to our final problem 6, adapt to on time. So here on time is being adapted with the input. So if there is any change in the input, on time will be accordingly adjusted. How? There is a fixed peak, and this inductor current is hitting the peak, and that decides my on time. So if the Vin is more, then it will hit faster, and if my Vin is less, it will hit slower. So this has high Vin, and this has low Vin. And depending upon that, on time is adjusted so that the peak is fixed. Again, this is like a trailing edge because my inductor current is below the I peak. So I have given V in, V out inductance and I peak information. I am asking the on time, and this is a buck converter. So we know that M1 is equals to V in minus V naught by L. From that information, I can get on time. And the delta V naught, someone has asked, as I told, this is a DCM operation. You should consider the DCM operation for delta V naught, and it will not have 8 below. Sir has shown the detailed proof of this. So the detailed explanation of the same is there in the session 3, online session 3. So sir has shown the mathematical derivation of the delta V naught, and using the delta V naught, you can so I told 1% output capacitor ripple. So output is 1.8. So 1% will be 1 by 100 into 1.8. So if I do into 10 by 10, it is 18 millivolts. So 18 millivolt is the delta V naught. And I have given L, I have given I peak, I have given V naught. You have to find the capacitance required to maintain the voltage within 1%. So this completes our today's session. So where we have discussed summary of the course in the first half, followed by a few problems. And I have not solved the problems. I have only given hint because these are discussed in individual weeks where we have discussed the problem solving and spent enormous time on that. So today I have only given like a brief explanation of how to solve, but you please solve as many problems as possible. And yeah, if you have any doubts, you may ask. Else, we can end the session.
Sir, in case of PFM or PW, PFM or PWM, like there is a mux operation, right?
There is a mux. Yes.
There are 2 muxes.
Yes.
From adaptive on time, we are getting QH high.
Yes.
Like QT on. And from peak CMC, we are getting 2 for QH and QL. Sir, while selecting mux, like for PWM, we have option 1, and PFM, we have option 0.
Actually,
or
PFM option 1.
It
can be done either way, whatever the way SR has done. For light load conditions, SR has chosen mux value to be 1, select line to be 1. In both the cases, voltage mode, voltage based multimode. In the case of PSL, the select line is 1. And in the case of current based multimode, PFM, select line is 1. And you are free to choose because it will still work, but you have to use it properly. So your code should tell the mux that the mode is 0 or 1, and accordingly the 1 or 0 should be sent out.
Okay. In assignment 12, there is a question based on this.
Okay.
For if we select 1, like if we select one, it acts for one mode correctly, and for 0, like there are two options available, sir.
Yes.
In which PFM or there is no information about PFM or PWM in that case.
Okay, I'll tell you one thing.
In the
So
question
if I have,
itself.
I understood which question you're talking about. So when there are two muxes, the select line should be the same for both the muxes because it is the
Yes, sir.
like in a single code. So if the select line is for say the select line 1 means it is for light load, it should be the same for both. And the select line 0 means it should be the for both. And are there any options like more than one which comes under this category?
Yes, sir. Actually, the same select line is given for both in both options. The same is given.
Yeah, like select line will be the same, but the mux input say, let me draw. So we are considering to say PWM PFM. This is PWM PFM select line. PWM PFM select line. And it has 1, 0. It has 1, 0. It has 2. One is for high side, one is for low side. So the output is QL here, or maybe I'll use a different color for output. And it has inputs as well. So my input says QH PWM. Here my input will be QH PFM. Here my input is say QH, and here it will be QL PWM, and here it will be 0, and here it is QL. Now if you see, in both the cases for 0 I have used PFM. Here PFM. For 1 I have used PWM. For 1 I have used PWM, which means when my select line is 1, high side will be coming from PWM, low side will also be coming from PWM. And when it is 0, high side will get a gate signal from PFM, and low side will also be getting from this. So the other way which SAR has done, so this I'd like to call SAR's way, it can be QH PFM. So for select line 1, you can give QH PFM. In that case, this should be 0 because when the select line is 1, both high side and low side should get the gate signals from the PFM operation, which is happening. In that case, this one will be QH PWM and this one will be QL PWM. Understood?
Yes, sir. Yes, sir. Like, can I share my screen?
Actually, no, like one thing you can do, can you ask this question in LinkedIn?
Okay, sir. Sure, sir. I'll share now.
You just drop it there. Then after this session, I'll address your question. So you just, if you have any confusion between two options, you just ask me. Then I'll let you know there. But this is the concept. If you have understood the concept, then it is okay.
Sir, here what you are saying, if it is 1, for QH PWM, like you are giving, if it is 0, as the thing. Yes, sir. I'm clear with the concept, but I'm getting two options there.
Okay. Then I'll check because I do not actually remember the option. So you just send a screenshot of the options which you are thinking could be correct. Then I'll resolve your query.
Okay, sir.
Yeah. So
Sir,
with this,
like for examination point of view, what are the concepts you have to
like you
focus?
should be thorough with all the weeks. Like there is no such important topic and not important topic. All the topics are important. You should be thorough with all the topics. But yeah, like you first, I would suggest all of you to do all the all the assignment problems. So you practice solving assignment problems, and you can do the calculation. I suggest you to do the mathematics because in the final question paper also there will be few questions where you have to do the math. So it will be like easy for you also if you start solving from now. So you go through all the lectures, and if you face any difficulty, either you go through SARS lectures or you can go through our discussion lectures. So and it will help you understand the concepts better and solve as many problems as possible. So 70%, 70 to 85% questions will be from the assignments as well as lectures, and it will be simple only if you know the concepts, if you have solved enough problems from the assignments, and if you are thorough with what you have understood, you will be able to solve 75 to 85% of the problems. But the rest 15% will be tricky, which again you will be able to solve if you have understood the concept clear. So that questions will be tricky, more of conceptual, not lengthy. Like the question paper will not be lengthy, but it will be like somewhat tricky questions where you might tend to make mistakes. So if your concept is clear, then you will be able to do it. But if you solve the assignments properly, you will be able to attempt 70 to 85%, I would say. Yeah.
Okay, sir.
Yeah.
Sir,
Continue.
nothing, sir, no doubt.
Okay.
I want to thank you for the time and effort you have taken for us
Yeah.
for the past 3 months. So your commitment is awesome, sir. Thank
Okay.
you so much.
Yeah, thank you
Yeah.
so much. And
We have the knowledge we have gained through yours. We have definitely made a change in our life.
thank you so much.
It will help in your job in the future. I hope we have learned a lot.
Yeah,
And
thank you so
all
much.
the best for your PhD also, sir.
Yeah, thank you. Yeah, this is my first online session. So previously I have never taught on a public platform. So yeah, this is my first time, and like I'm trying to improve myself as well as and all the sessions that we had, they were actually quite good, and you are asking so many good questions. So it is bringing interest in me to teach you more. So sometimes we have even gone beyond 2 hours, but all the sessions I really loved, and every day I was looking forward to our Monday session, and yeah, like it was a quite great journey all these 3 months have been, and yeah, I wish you all the best for your exam as well as your career, and we can stay in touch, and you can stay in touch with professor as well. You can contact the professor. You can contact me at any time through mail or LinkedIn, and yeah, we we can stay in touch. Yeah, and I wish you all the best for your exams, and I hope my sessions could be could make some difference in your preparation, and could make you understand the concepts in a better way. Yeah, okay, then
See
with
your
that,
sessions in the forthcoming weeks, sir.
sorry.
No, we'll be missing your sessions, sir, in the forthcoming weeks.
Okay, yeah. Maybe we can meet when
Bye,
we
sir.
take some other course in some other semester. Okay, yeah.
Good night, sir. Thank you.
Yeah,
All
good
the
night.
best, sir.
Yeah.
I
Thank you so
also
much.
want to thank you. Though I'm working in an organization based on power electronics, I don't have this much knowledge during my 1.5 year.
Okay.
But during these 3 months, I came to learn a lot through your support majorly. Your patience is very nice, sir. Though I contact you at any time, you respond as soon as possible by clearing my concepts. Thanks a lot, sir.
Yeah, thank you so much.
You
And
really made a like milestone in my learning journey
okay, yeah, thank you so
before
much.
this course and after this course.
Thank you. And
Thank you, sir.
yeah, like whenever you ask questions, it also makes me think it does not mean that I know everything. So when you ask questions, it also makes me think, and maybe I'm not able to solve, but it keeps me pushing to learn more and achieve more. Yeah, and this session has been quite a journey to me as well, and because this is my first time, and yeah, I'll remember this session
Sir,
because this is the first time.
sir, in LinkedIn, how to be staying in touch with you?
Like we can make connections. So like you can contact me through LinkedIn. We can chat through LinkedIn if you have any queries or if you want to discuss something. Yeah, I'm up for discussion.
Sir, can we search you with your name itself?
Yes,
Teja Golla.
actually. Okay, then one thing I'll do when I upload this session in the YouTube, in the description, I'll mention my LinkedIn ID. Would that be good? Or you can search Teja Golla, TJGOLLA, IIT
Yeah.
Kharagpur.
Yes. Okay.
Okay. Yeah, thank you so much.
Sir,
Thank you for your compliments.
sir,
Yeah.
sir, could you please explain the concept of like volt-second balance doesn't holds good during the transient condition, right?
It will, sorry, volt-second balance? No, like when you like
Like, sorry, volt-second. Okay.
uh,
Okay.
volt-second balance.
Yes, sir. Or volt-second balance for an inductor or charge
Balance.
balance for capacitor.
Conduct. No. Sorry, capacitor. Yes.
During transient, it doesn't holds good. May I know the reason for this?
Like you cannot say that because of the controller it is happening in that way, because that undershoot is coming because of that external, because when we talk about steady state, no such external force is being applied on the converter. So the net charge that it gains and the net charge that is being discharged will be the same. Whereas in the case of transient, when you consider a load step up transient, there is an increment in the I node, and this has to be provided by the capacitor. So there is a cause because of which this is happening, and that's why. And again, after steady state, it will move to that steady state. But because of that action, that trigger, that I naught is coming, there will be a dip in the capacitor. And that additional charge is going where? That additional charge is getting converted into that I naught. Understood?
No, sir, not yeah.
Okay.
What's the point?
Like when you stay at a steady state and nothing is being applied, the capacitor charge remains at certain value. And if you consider the ripple, whatever it gets charged, it will get discharged during the off time. Whereas when there is a low transient, so you are forcefully drawing some current and that inductor cannot provide, so the capacitor will provide, because of which there will be a undershoot or like dip in the voltage. So there is a charge that has been taken from the capacitor, and where is it going? It is going into the output. It is not that like some charge is being created, but it is getting distributed, and then slowly inductor will provide that charge. So at that instant, capacitor is provided, but later the inductor will be delivering that current. So again, capacitor will come back to its voltage. So during that transient, like whatever the energy that the output needs, it is being supplied by the capacitor, which again is slowly getting transferred to the inductor. And when again it reaches the steady state, now there is no disturbance. It will still be balanced. But at that instant, some external disturbance is coming. So for that requirement, capacitor is giving the charge. So for that purpose. When we
Okay, sir, it is clear now.
yes, so when we again talk about the input-output voltage relation of buck converter, say V naught is equals to D into V, then we consider the steady state, because we want to find the steady state relation between D into V naught equal to D into V. And again, this is a good point Shankar has asked. When you consider a buck converter transient operating under closed loop, when there is a increment in the inductor current, or when there is a load step up transient, V naught is dipping. And if you consider at that instant, I naught is increasing, which means duty ratio will increase, but output is dipping. So you should not consider V naught equal to dV during the transient. It is applicable only at the steady state. The same way, whatever we do in the steady state, the charge balance, it is for steady state, for that purpose only. Because during the transient, controller is taking the action, and you cannot say that D is increasing and V naught is decreasing. During the transient, it is not applicable. It is applicable only during the steady state. I hope that
Okay, sir.
that clears your query.
Yes, sir, clear.
Okay. Okay, then all the best to you, for your final exam, and we can end this session. Good night and all the best.
Thank you a lot. Thank you a lot.
Thanks, sir.